All right, hi everyone. So I'm Fabien Chouteau, working for Ada Core and property-based testing in Ada. The missing 10%. Okay, so this project starts with me reading this blog post, which is about monads, but that's absolutely not the point. Because the author is using a Rust property-based testing library to explain the concept of monads. All right, and so that's how I discovered this concept of property-based testing, and so that's just the starting point. Next slide, please. Developer deciding on a formal specifications that they want their code to satisfy, encoding that specification as an executable property. And the second part is automated test harness to check the property against their code using hundreds of thousands of random inputs automatically generated. So if you already know Ada, first part is quite easy, right? Because that's more or less built in the Ada language. I think next slide we have some random example of something absolutely useless, but yeah, within Ada we have all the power to specify very powerful and very precise properties for our program. And so using the type system, using contract-based programming, and so on and so forth. So from this, you can say that Ada is extremely compatible with property-based testing already. And we are 90% there, but we are still missing the second part, which is automated generation of random inputs to the properties. Next one. So at Ada Core, we developed a couple of tools that are bringing that second part. One of them is GnatFuzz. So GnatFuzz will very rapidly generate new test cases and test the code against those test cases. It's quite a smart tool that will analyze the path taken within the code to try to improve the reach of the various mutations. And so it's not just randomly picking test cases, it's actually better than that. It's going to improve the test cases, mutations after mutations, to try to reach every part of the code. So because of this, it's gonna explore deeper into the code, basically, because if you have, I don't know, if you have a check at the beginning of a function that will half of the time raise an exception, if you just randomly generate inputs, it means half of your generated test cases will just fail, and that's pure wasted time. So that's a very advanced tool. It's a relatively new tool in the portfolio. Next one. So yeah, for those just an example of things you can test, obviously. But yeah, the idea is that with a tool like GnatFuzz, it will go deep through the various nested loops and conditions to explore various paths of the code. Just this week, I learned about a new feature as well. If you go to the next one, which we are adding to GnatTest. So this is relatively new. I think it will be in the next release of GnatTest, if I understand correctly. We call this tgen, and it's gonna, so it's a bit more lightweight than GnatFuzz. It's gonna analyze the source code, so analyze the types, to generate random test cases that would fit. So for the example before, this is going to generate an array with the first and last index. And so you have test cases that are stored in files, and that can be replayed later on if they trigger an error. Typically, you want to replay those tests. So that's going in GnatTest very shortly. So those are two tool-based solutions, which are mostly automated and very industrial-oriented solutions. On my side, I wanted to explore something similar to the original prop test library from Rust or Quick Check from Haskell, which are implemented the property-based test features in a library format, not as tools. And so this is why I started the strategy project. So strategy, it's an open source project. It's a crate on Alir, so you can use it very easily in your project, in your testing. So first, I'm going to show a basic example of how to generate stuff with strategy, and then we'll have a look at how it's actually designed and how I ended up making the library the way it is. And then I think we do a more advanced example at the end. So here, maybe we want to check a sort algorithm, right? So very basic stuff. I have an array type, indefinite array type of unsigned 8. So first, I have to instantiate this indefinite value tree package. So I will explain what this is later on. Then I instantiate a strategy, indefinite array strategy. So I give it my element type, index, the array type itself, the value tree, and I also give another strategy, which is the strategy to generate the elements within the array. So I have a strategy for the container and strategy for the elements within the container. If you go next, then we just need to sort function. So I'm just using the generic array sort from the Ada standard library. Then we need to provide a function that will check if the array is actually sorted. So that's going to be the oracle for the testing. So it can be anything, but here it's just checking the array is sorted. So very, very basic. And then start to reach the end of the usage. So we instantiate a runner. So the runner takes a strategy as an input. So how to generate values that we are going to test. It takes the function that will check the actual function, the actual code that we want to test. And then we just start the runner, we get a result. If the outcome is fail, which means the library found an input that fails with the sort algorithm. So in practice, this is not true because the implementation of sort in GNAT is good. So I'm not going to find an error, but just for the example, we can print the result that triggered this failure. We can also store it or put it somewhere and keep it for later to rerun the test, and then we free the input, and basically that's it. So I think, or maybe it's just below, we don't see it, but there's an example. It's just, yeah, oh, yeah, that's perfect. This is an example of an outcome. Actually, I implemented another sort function that doesn't work when there's a odd number, something like this, just to trigger a bug, basically. And so what you can see here is the result of the process, which is very important in property-based testing, which is the simplification of the test case. Basically, what we want, because everything is automatically randomly generated, it can be very complex inputs, which are basically have no sense. So the library will do its best to simplify the test case as much as possible and find the simplest test case that triggers the bug. And so, for instance, so here we have an array of unsigned integers, and so the simplification for integers is go towards 0. And so the simplest test case for the bug that we are trying to show is an array of zeros and just one odd number. All right, so that was the first example, and now let's see how to actually design and implement the strategy library. So first, one thing you have to think about is that we can create arbitrarily complex tree of value test case generations. So we combine the different strategies. We have a strategy for vectors. We have a strategy for tuples, which are just producing records. We have a strategy for enums. We have a strategy for arrays. We have strategies for unsigned numbers and so on. And we can combine them to create this. At the end, we have a complex test case, which is a vector of tuples of enums and arrays of inside integers. And of course, you can do whatever you want. You can mix everything. You can create your own strategy. So this representation is called the value tree. And the first step is to define the interface for the nodes of the value tree. So this is the first part. We have an interface with two functions, simplify and complicate. So that's what internally does what I mentioned, the simplification of the test case. So for every node, we should be able to simplify the value and then complicate backup, which is first you try to simplify until the bug is not triggered anymore, and then you complicate back up to find again the value that triggers the bug. So for instance, for the integers, it's going to go towards 0, and if the bug is not triggered anymore, it's going to increase until you reach, for instance, the 23 in the example before. So that's common to all the nodes. And then we start to go into the generics, and it's going to be a lot of generic instantiation here, so bear with me, because we also need to get the value, of course, of this node. So we have this package, and also, so we have basically two versions of this. I'm just going to look at the definite value tree, but we have the same for indefinite. And so this one is just to have a function that can actually return the value, and this we need polymorphism, so we need a generic packages. We don't have generic types. So we have this package that we have to instantiate to declare that there's a value node, which is a node of our value tree that can return this type of value. All right, let's go to the next one. This one is interesting. Actually, Stefan, it's a bit like what you explained before. I'm calling this trait generic. This is, I mean, the first time I've heard this is from a former colleague, Manuel, who worked on the ADA traits containers, I think. So this is kind of similar to the idea of traits because it's an empty package. There's nothing in it. It's just a collection of types and operation on types. Why is this useful? Is that because we can then later on ask users to provide instantiation of this package to other generic packages, and so we basically get some form of capabilities for a type. So what we want is the value, the instantiation of the value tree, so we know the node type, an implementation of the value node, and a function to create that node. Okay, so that's what we call a strategy. If we continue, let's create a strategy together. So of course, it's going to be more generics. So we create a modular strategy. So we need the value type that we want. We need an instantiation of the value tree. And then we start the implementation. So we derive the node type from the value tree value node. We implement the create function that we need to create the node. We implement the three node functions, so to return the current value, simplify the value, so I'm not showing the code, but this is just going towards 0, complicate going back up. And then we provide an instantiation of the definite strategy, so the thing we just saw before. We provide the value tree, the node, and the function to create the node. All right, and so now we can use this strategy. All right, so now that we have our modular strats, so it is a bit like before, we instantiate the definite value tree for inside 8. We instantiate the modular strategy, and now we have this strategy that we can use for within other strategies. So here we combine the different strategies. And this is what where the traits package is actually useful. When we define a tuple-like strategy, we just ask the programmer to instantiate and provide instantiation of definite strategy. And so here it can be absolutely anything because we are using this trait generic system. So you can put a tuple strategy within a tuple strategy, or an array, or modular, Boolean, enums, whatever you want. And this is how you can create this indefinitely complex tree of value generation, which will automatically handle the simplify and complicate part of the property-based principles. All right, I think we are going to have a look at the runner itself now. So the runner, it's a package that will implement just the part to basically generate a test case, check it against the test function provided by the user, and if the test function returns false, which means we have found a problem, a bug in the algorithm that we are checking, then it's going to start the process of simplifying and then complicating again the test input. And so this is going to propagate through the value tree. So if you have, for instance, an array, you want to simplify each element of the array, and for tuples, you want to simplify one element and then the other, etc. That's part of the implementation of the strategies. Basically, part of the strategy is how you generate a random test case, but also how do you simplify and complicate it. That's very important. So again, we use the definite strategy trait-like generic. So to run a test, you have to provide a strategy, a function that checks the values from this strategy, and then you can either run just one test with a seed. So yeah, I forgot to mention that, but in the result you also have the seed from the test case, so you can just save the seed and regenerate the same test case afterwards. Otherwise, you just run multiple and hopefully find one that fails. Okay, I don't know if we have much left. So that's same example as before. Implement the function that checks the value, instantiate the runner, and run the tests. All right. And so that's the end of the presentation. Have a look at the project. Have a look at the examples. I think in theory it's working pretty well because we have all those nice things in Ada to do polymorphism, the generics, and so on. In practice, it's a bit heavy because there's a lot of generics instantiations and all of that stuff. But in the end, it's a working solution, so I'll give it a try. It's in just a beta, prototype library. So have a look and let me know if that's useful. Thank you. Any questions?
A couple of minutes for questions.
Two things. One, you use tick IMG, and I presume tick image would also work. There was nothing special about using the Gannett shortened image attribute.
It's just what I'm used to.
Okay.
But then, yeah, I'm using what's nice with the 2022 image.
Generalized
you can
image.
Put it on everything, so it's nice to get the test case.
And then I think just in terms of heaviness, you might be able to remove one of the parameters in your strategy. Because the first one is value. The second one is a formal package that has it as the formal. You can refer to that formal package instead of passing in values.
So the thing is, when you are using that many generics, imbricated and so on, you will likely run into areas that not many people have explored before, and you may find
some Gannett bugs.
Gannett bugs or things like it's not sure is it legal, is it not legal, and so on. Actually, we during the process of writing this library, Eric fixed one problem with which is kind of similar, something that was Gannett said was not visible, but it should be. But yeah, maybe I could simplify some of it.
It wasn't just in general. When you get a formal package, you can refer to all of its components.
Thank you. I have a question. This tool is mostly useful where Spark cannot be used, I suppose, because as far as I know, Spark can systematically check all possible inputs and outputs. And
there's nothing. The basic Spark will it's a formal verification, so there's nothing that if you proof your code with Spark, there's nothing that this will detect basically. So it's another technique for checking your source code, and the same for gnatfuzz and gnattest basically. So it's just another way. So yeah, if I can compare the various solutions, because I mentioned gnatfuzz and gnatest, the strategy library, of course, it's very manual things. You have to think about the strategy, instantiate all the package, think of everything, which may lead to actually you may have a bias towards, oh, I think my algorithm can fail in this way, so I'm going to generate a strategy to check that, but maybe the bug is somewhere else. Where Spark, gnatfuzz, well, Spark you prove everything. gnatfuzz and the gnatest TGN stuff, they do not think like this, so they will explore more potential bug, more areas. So it's a different thing. Yeah.
okay, thank you. Are there more questions? Maybe online?
All right.
Then thank you very much.
Thank you.